spoke about what hypotheses are. Sorry, how we go about testing hypotheses around the means. So we have different populations. They have certain means, and that mean can vary a little bit because the way we sample the population can generate a distribution of possible means. So if I'm sampling hippos and elephants, I can, by chance, randomly select, if I'm sampling 10 hippo masses relative to elephant masses, I can actually randomly sample 10 very heavy hippos or 10 very light elephants. And so I would deviate from the true mean of the population like that. So this is what generated those distributions and those probabilities that we actually get a mean that is really far from that ideal mean or the true mean of the population. So we have a standard deviation that kind of tells us how those distributions occur. And now we want to know whether hippos and elephants are different in their mass. So we have to overcome the fact that actually when I take my 10 samples, I can get a whole range of means, and I need to know whether those randomly selected 10 heavy hippos are really different to those randomly selected 10 light elephants. Right? So we use the t-test for that to test for differences in means, and the t-test's power, the power of the t-statistic came from, we looked at the number of samples that I'm looking at. More samples, more robust the t-test, it's more easy to detect differences in means. The smaller the variance, the smaller the standard deviation around the mean, the easier it is to say this is one mean and this is another mean of the population. And finally, the actual difference, the true difference between the means, if it's the effect or that difference between elephants and hippos, is going to be very easy to detect if they are so very different. So an elephant and an ant, it doesn't matter how varied, I don't need to take a lot of samples, I will detect the difference just because the effect is so large. So we had all sorts of hypotheses, and these are those distributions we're talking about. So we have a t-test in this case, and a t-distribution, which we said looks quite much like the like the normal distribution, only slightly skewed, and the shape of that distribution really varies with degrees of freedom, which was the number of samples minus 1. Now, what we see here is this is the mean possible t-value for the true mean, and these are kind of the range of possible t's I can get by randomly selecting 10 different hippos and 10 different elephants. So here are my two distributions, and I want to know, are they different enough? And we take a significance value, which is our critical value, and we say, okay, I'm going to say they're different. Okay, I'm going to reject my null hypothesis, okay? And sometimes when I tell you that, there's still a chance that I'm wrong, okay? And this, we call this a type 1 error, that I've declared a null hypothesis is void, yet actually it isn't, okay? So what I have to do is to say, okay, how sure am I that the null hypothesis is, that if I reject it, I'm correct, okay? And I want to be right 95% of the time, okay? Because I've decided my alpha value, my significance value, is 0.05. If I decide differently, if I'm studying physics, for example, I want to decide my alpha value, my significance value is 0.01, is 1%. I want to be wrong only 1% of the time. In our disciplines, it's mostly 5%. Okay, I'm allowing a 5% error in each test. Okay, so I want my t, the one I calculate from my data, to really exceed the possible t's of a true null hypothesis of two populations that are the same. So I would see something like this. This is my distribution, And the area under the curve, like we said, is 1. And I want that 5%. So 100% under the curve, 2.5% to each side. Okay, and I want to make sure my value is really different and does not sit. It exceeds that critical value. Okay, so we looked at the t-test, and like we said, we have the differences in the means are important, the standard deviations are important, and the number of samples is important. So you remember we talked about those critical values? You can plot them, or you can put them in a table, and this is in a table. Okay, so for 0.05, if I have, remember the distribution looks different if I have different amounts of freedom. So if I have 30 samples and I have 0.05 as my critical value, I need my t to exceed 1.697, so I can say I am rejecting the null hypothesis with confidence. I'm significantly rejecting the null hypothesis. The chance that I'm telling you that and getting it wrong is less than 5%, so trust me, right? We looked a little bit at what the t-test does in R, and we'll practice this in class, it might be better. But what we had to write is the function t.test, and of course the two data sets you're comparing. The t-test is only comparing means of two populations. When we wanted more than one population, we went to ANOVAs, and we'll talk about those a little bit more. We spoke about paired and unpaired. Okay. And then I came onto this table here, and this is a slight cheat sheet. It's good to remember when you're comparing one group only, you're only interested in a mean, and to know whether a possible mean that you've invented, say the weight of bread, belongs to your population of breads. Okay, so we're not comparing breads from Woolies to breads from Coles. We're talking just the breads from Woolies. Are they different to the standard, or the Australian standard for bread size? Okay, so that was comparing one group to a hypothetical value. So in R, what we would do is, instead of writing out two populations, we would write out our population, and here, instead of a whole population, we would have a population of the same value, right? We had paired and unpaired t-tests, and then we spoke about having more than two groups to compare. And with that we did ANOVAs, and we'll recap that in a second. Now this is all for data that is sort of normally distributed, so of course continuous data. Things that are not normally distributed have similar tests, we'll come back to those later. And things that are not just continuous data, but rather binomial, what we call the binomials, the yes, no, present, absent, have their own tests. And I'm going to recap analysis of variance. So we keep talking about a mean of a population. So here's group 1, population 1. Group 2, population of samples 2. Group 3, population 3. They're normally distributed, right? We're in that column. They all have a mean and a standard deviation around the mean, and that's what's determining the shape of this curve, right? Now I'm asking myself, are group 1, 2, and 3 the same or different, right? So remember, it's the omnibus hypothesis, so I either have all the means are the same, or no, all the means are not the same. It's enough that 1 is different to 2 and 3. 2 and 3 might be the same, but 1 is not the same as them, so I'm rejecting the null hypothesis. Okay. Now what I'm interested in is, in an ANOVA, an analysis of variance, is the variance. So I have a variance, I have two types of variances here. I have a variance that's within the group, so how much the group is spread around its own mean. And then I have variance that's between the groups. How different are the groups from each other in that parameter I'm testing? So that's the omnibus. Once we have more than two populations, you cannot run a t-test again and again and again. Now, this is because, remember we said, I'm going to tell you with some significance that I've rejected the null hypothesis, then I might still get it wrong, right? I have a 5% chance of doing that. If I do that once, I have a 5% chance of doing that. When I do that twice, I have a 10% chance of doing that. If I do it 3 times, I get, eventually I'm going to get to a test that gave me the wrong answer. And I'm avoiding that. I'm trying to develop a test that does not need to be, I don't need to take the risk of being wrong more than once. So here are my between group variation, okay, between the red line and the blue line and the blue line and the yellow line. And then I have the within, the between and within variations, okay? And the idea behind the ANOVA, remember we said, is that if the two groups are quite different to each other, even though there's a variance within the group, the variance between the groups is much greater than that, okay? So we spoke about knowing that cows are cows and humans are humans, even though humans are incredibly diverse creatures, as are cows, but the diversity, the variance within each group is much smaller than the variance between the two groups. Okay, we walk on 2, they walk on 4, they're very big, we're not that big. Some people are, well, never mind. Okay, so I have developed, like with the T, which had parameter, that is a statistic that really takes into account just the shape of the distribution and the number of samples. This time I have a test variable that's called F, okay? And F is a ratio of this variance overall, okay, to the variance within the group. And the variance within the group is, the bigger it is, the smaller the F. Okay, so I can already tell that F gets bigger when my groups are more different from each other than they are within themselves. Okay, so I want a bigger F. How big an F? This is what the F distribution is telling me. Where is my critical value if I want to remain with a significance value of 0.05? The F distribution again is sensitive to the number of samples. So what we have here are different F distributions. And what this means is basically that when I look at that curve and I cumulative get to 100% under the curve, where 95% falls, it really changes. Okay, and that's why it's so important to know your sample sizes. So we looked at the ANOVA test and we said, okay, there's an A horizon, a B horizon, and core stones in a soil core. Okay, so this time we're comparing things. We can compare things across these 3 different layers. So we have 3 different populations of samples. We very quickly run out of only 2 comparisons. Almost everything we do starts being a comparison of more than 2 things, and that's when ANOVA comes in. So in this case, we went over it in the previous lecture, but we have in the back swamp, we have 3 sites that Vanessa Wong sampled. She sampled a few horizons, but we're going to stick with 1 horizon. So, and what we're interested in are these continuous variables here, like pH and redox potential and salinity. And they're replicated, okay? So we've subsampled the potential entire population 3 times, okay? So that's not a lot. We have 1 factor here, which is site, and it has 3 levels. So 3 different locations. We have a continuous variable, say pH, and we have the number of samples at each site is 3. Now, if I want to know how this factor, this single factor, affects pH, then I have what's called a one-way ANOVA. I'm only looking at a single factor. If I wanted to look at additional factors, say this table kept going and then also have horizon B, I can add factors to the ANOVA, and I can have a 2-way ANOVA, a 3-way ANOVA, a 4-way ANOVA. I can add, if I have enough samples, quite a lot of factors. But we'll start with 1-way, okay? So what I want to know is whether the variance overall is different to the variance within the group, okay? So if it's overall, the variation between the groups is the same as the variation within the group, which means I can't tell them apart. And what I want is an f that's greater than 1. It's differences between groups that are greater than within the group. It's not enough just to be greater than 1. We need to go back to that distribution and work out what our critical value is. So I do it using R in this way. I have an analysis of variance. It's called AOV. And this time I have an equal sign rather than that arrow sign. And that's because they're kind of interchangeable. So I've put this as an example. And pH is my variable that I'm interested in. Okay, that's my measured variable. And I'm looking at it, and this funny line here, the tilde, which you do with the shift, right, is as a function of, in this case, site. Okay. And what I have here, data equals soil, is just telling my computer, my script, where is this data set? What's it called? Okay, so you say pH and you say site where. What's the name of the data set? So that's in soil. If I open soil, I'll see that there's a variable called pH, there's a variable called site. And if I run a summary of Q, I call it Q. I can call it whatever I want. I can see that site, there are 3 sites, has 2 degrees of freedom, right? Because we said the number of degrees of freedom minus 1. And it has variances, and from these variances an F value is calculated. Not a simple calculation, right? It's not just this divided by that, okay? It's sort of this divided by that. It's a bit of a, but we have a F value of 2,722. It's a very huge F value. I'm going to reject the null hypothesis. It exceeds the critical value with a huge probability, with a incredibly significant confidence. So I have here something that's almost close to 0. The probability that I'd get an F value that's bigger than that. Okay, so I am so very confident. Now remember, my criteria to accept my rejection of the null hypothesis is to have 0.05. A P of 0.05 or less. I am way less. Okay, so there's 3 stars here because it's very highly significant. So I'm going to reject the null hypothesis. The pH is not the same among the 3 sites. However, all I know is that it's not the same. I don't know which site made it different, right? All right, so next one we're going to go to chi-square, but I will